So the outline of my talk is very simple. So I will first discuss the problem statement. So what is the differential equation and by what sense we mean to solve this problem. And then I will discuss about the challenges together with the previous approaches. And then I will discuss my result, our result, and how we sort of conquered these possible challenges. All right, I'm going to start by discussing about Hamiltonian simulation. We all agreed yesterday during the panel that this is possibly one of the most near-term applications of quantum computer. So the definition of this problem is very simple. We have a Hamiltonian, say a Hermitian matrix, that is of size 2 to the n. It can be time-dependent in general. And then the corresponding Hamiltonian simulation problem says that we have this Schrödinger equation, the differential equation basically, with an anti-Hermitian coefficient matrix essentially. And the task is that we want to prepare a quantum state that is our final solution within certain procedure. We know that there exists great works already, and there are various different approaches that can give us the optimal scaling essentially. By optimal, I mean that the state-of-art cost for this time-dependent Hamiltonian simulation problem can be linear in t, which is the time that we are considering, and can be log in terms of the precision. And this alpha h comes from the subnormalization factor of h, which is a quantity that is larger than the norm of h. You can view this norm of h coming in linearly. And the assumption to achieve this log in precision linear in t, generically in the setting is that we need the boundedness of the first derivative so that we can make any sort of quadrature argument to work. All right, so now I want to basically take a look at of this picture. So we're basically sitting here. We have a Hamiltonian simulation, which is a very important problem. So over the years, people trying to sort of go beyond this circle and make the boundary maybe a little bit fuzzy. We have seen yesterday the whole day is about open quantum systems, so maybe we can go beyond a little bit. Or more generally, it's of people's interest to consider linear differential equations. So you can see this is a particular case of the linear differential equation where my matrix is anti-Hermitian. Or can you consider general differential equation? I would like to say the first work of this field is really coming from one of the co-organizers, Dominic Barry. The first preprint was back in 2010, so you can imagine we already have more than 1 decade of history trying to solve this differential equation problem. Well, now I'm just going to give you the definition of this differential equation problem, what people are trying to solve. Basically, we are just looking at these general cases where A is no longer anti-Hermitian, and it can be a general time-dependent n by n, 2 to the n by 2 to the n matrix. And the task now changed to we want to prepare a quantum state that is proportional to the final solution, because we know for general differential equations, the underlying dynamics may not be unitary, so the norms may not be preserved. So correspondingly, the precision we need is really, if we get something, we want to sort of normalize it, go back it to a quantum state, and we want to ensure, in that sense, the error is small. So you can notice that similar as a Hamiltonian simulation case, you can write down the exact solution. Then sort of the what we want to do at least is to construct a efficient circuit to implement this timing the time ordering operator. So this is the definition of the problem. You have also seen many motivations of this problem in this morning. I will not repeat those motivations. So this will be the problem that I will focus on for the rest of the talk. All right. Now let's try to discuss about the challenge. Or as I said, we already have over a decade of history solving this problem. So what are the challenges? Now let's think, I want all of you think yourself. Suppose maybe you are either an applied mathematician, maybe numerical analyst, or maybe you are computational physicist or computational chemist. Let's think about if you have a differential equation and you want to solve it classically, what do you do? I have a differential equation that is evolving in time from 0 to capital letter T. What do you do? Right? I give you 3 seconds to think about this question among yourself. I think basically what we all do classically is that I have a long time. I'm going to chop it into small pieces. And then for each of the time step, I will use this so-called time marching strategy, which is I do a numerical integral a numerical integrator at this short time step so that from the previous step, I have a closed formula to the next step and so on and so forth, right? So step 1, we chop into pieces. Second, we can choose any arbitrary numerical integrator as long as it has good, say, consistent property, it has good approximation, and then you can piece these together. This is a general recipe for us to design algorithm, and you get an algorithm. So I want to say that this time marching strategy is really the foundation or the starting point for nearly all classical algorithms. As well as if you think about how we design the quantum algorithm for time-dependent Hamiltonian simulation, we do the same thing. We chop it into small pieces, and then maybe we can do a truncated Dyson series in order to get the optimal scaling that I show you on the first slide. So there are various different numerical integrator you can take. Well, it really doesn't matter which numerical integrator you take. Any integrator, reasonable ones, you can all make this strategy work. Here, I just gave you some examples for my numerical analyst friend. This is a forward Euler. You can also do a backward Euler, and so on and so forth. Maybe you can also do an exponential integrator. You can do a Magnus integrator, symplectic integrator. However you like, you can choose. This short time integrator is of your choice. You can choose your favorite one. All right, so far so good. Then you may wonder, well, I just use this quantum layer and I change it into a quantum circuit. What's wrong with it? I should have a working algorithm, and why do you still study this problem, right? So the issue is that I'm going to take the forward Euler as a concrete example. If you look at other numerical integrator, it's almost the same, the same argument. So for this simple example, now because the underlying dynamics is non-unitary, and also at the same time for generic A, the density matrix that follows may not be CPTP. So if you really look at this, it's really something that is highly non-unitary. So you really need to do a block encoding. So there, I guess after this week's workshop, there's no need for me to convince you. You need some form of block encoding. Now let's think about if this is a numerical integrator, how do we do a block encoding? I just want to sum two things. I can do a LCU. Right? Then the subnormalization factor you realize will be the L1 norm of these coefficients essentially is 1 plus delta t norm of A, which delta t is a short time step. This is a quantity that is guaranteed to be larger than 1. Are we okay so far? Okay, now let's just say, okay, I have this block encoding for my short time integrator, and I have L different time steps, and then I can just use the properties of block encoding or the QSVT by the authors in this audience. I can construct products of block encoding, which will give me a solver. What's wrong with that? If you really do that for this naive example, you immediately see the subnormalization factor become multiplied together. There are L time steps in total. In other words, the subnormalization factor have an exponential in L blowing up. Well, you may be like, why this become an issue? And then you applied it to a state, the success probability will be exponentially small. This is why historically in literature, people has viewed this time marching strategy to be something that is infeasible if we want to implement it quantumly. All right. Now at this point, you may not buy my argument. Say maybe you may want to ask, well, if this is something related, issues related with success probability, maybe I can just do amplitude amplification. Well, if you are working on dynamics problem, you immediately know this is not possible. But for other friends, let me just illustrate why this is not possible. If you do amplitude amplification, boost the success probability at each of the time step. Let's recall what amplitude amplification needs to do. You need to have a reflection around the state that you start with. Well, how many times you need to do amplitude amplification is guaranteed by the success probability, which is a quantity that is guaranteed to be less than 1. Now let's imagine at each of the time steps, suppose I need 2 previous access to the previous state, the state that I start with. Then the next step, I need 2 of the previous, hence 2 square of the previous time step. How many time steps are there in total? There are L time in total, hence you easily get exponential in L access to the initial state access. That's, again, exponentially blowing up. That's why you do not want to do it in this procedure. At this point, maybe many of you will be rolling your eyes. You will be like, it doesn't make sense. Well, we do this all the time for Hamiltonian simulation. Why does Hamiltonian simulation work? right? The thing for Hamiltonian simulation is really that the underlying dynamics is essentially a unitary. There are certain structures you can use so that this amplitude amplification proposed by some of the speakers and together with collaborators of this workshop, so that you can do it in a way that is oblivious from with respect to the state that you start with. You do not need to do a reflection around the state. In this way, you can make it work. All right. But generically, if you do not have OAA, you cannot make it. It's not so clear why it is going to work. I hope so far I convinced you that in order to make things to work, it's really the bottleneck for these solvers is that if I have short time integrators, how do I piece them together in long time? And the naive piecing I showed you will not work. All right. Here, I want to just say a little bit about a side note. So throughout my talk, I will mainly focus on time-dependent problem. You can also ask, what about time-dependent problem? I would like to say maybe this is sort of easier. Well, you can do the same thing, but it might be sort of easier. For example, if it's time-independent, on top of that, A is anti-Hermitian, they are going back to the time-independent Hamiltonian simulation case. We know that the best scaling can be given by QSVT, for example, and it will just work by the audience in this room. And then you may wonder, what about general A? Shouldn't just QSVT work? I just applied the similar idea. Well, it's not anti-Hermitian anymore. Maybe I can still use QSVT. What's wrong with that? Well, there is a slight note that you might notice immediately is that QSVT is doing the singular value transformation, which is changing, you are applying a function to the singular value part alone. However, if we talk about matrix function, they really agrees with eigenvalue transformation. So you are performing the singular value transformation, they may not be the same thing as the eigenvalue transformation, which is indeed the case here. But there is a natural remedy to this problem. You can also find it in many papers together with our appendix, is that if you want to really want to do it general and you can still, for time-independent case, you can still sort of do QSVT, it's because if you go to a complex analysis, there is this simple contour integral formulation. Well, this essentially is telling you that instead of doing a matrix exponential, you can turn it into a bunch of matrix inversion problem, which we know that there are optimal matrix inversion techniques that you can solve these problems. And I highly recommend you to take a look at the tutorial talk of IPAM given by Dong'an, which discuss how to solve that. Then maybe you can still be kind of not believe me because, well, 1 over x, this is still a matrix function. You may ask me like, isn't this matrix function still agrees with the eigenvalue? Why this particular matrix function, you can use singular value instead of eigenvalue? So the intuition is actually very easy. It's really just because if you write it in the singular value way, and you can write out the inverse, which is exactly in this expression. And then you take a look at it, you transpose this, you get V in the front U, and then you apply the QSVT, which gives you a sigma inverse in the middle, which is exactly the inverse as you like. So this, I just want to say the linear systems function is so special so that this QSVT will just work, no problem. Okay, I hope this is okay so far. And please.
What is the contour here? Is it,
the contour is something that you need to choose in terms of for example, you can choose a rectangular contour or you can choose a radius, a circle. In our paper, we choose a circle and it's sufficient.
Which contains all the eigenvalues inside or something?
Yeah, that's right. That's very important. You need to contain all the eigenvalues inside. Any other questions? Please.
So the anti-Hermitian part is the best asymptotic scaling, and the Hermitian part, if A were Hermitian, then it's.
Yeah, that's a great question. So when will the singular value decomposition agree with eigenvalue decomposition? As long as the underlying matrix is normal. So if the underlying matrix is actually Hermitian, you can directly use singular value decomposition. You don't even need to do a contour integral.
Because I could split my A into anti-Hermitian and Hermitian.
I mean, if your matrix is either Hermitian or anti-Hermitian, you can directly use QSVT. For general cases, you can use this formulation instead. You do not need to split it into a Hermitian part and anti-Hermitian part.
But that wouldn't be more more efficient splitting it into?
Yeah, this is already good. Yeah, that's a good question. Any other question before I move on? Please.
So when small s is large and the special norm of a is also large, I guess the contour should be also large.
Yeah, that's right. That's right. It's governed by the time of the evolution. As you imagine, if there is a time, and then it will come into the cost.
Then how is a large k scale with a small n probably?
Large k still the k with n. What is n? The 2 to the n, the little n.
N is number of qubits you are using.
Yeah, actually here we are saying that, okay, we are supposing we are given a oracle access model of A, which is already in a block encoding form. And then these are sort of independent of how many queries you need to call this oracle is independent of the number of qubits n. Versus then you can ask, how do I construct this oracle? Suppose A is as sparse, then we know that we can construct using subnormalization S, where S is the sparsity. Yeah, thank you for the question. Please, Lux.
If I know that I'm in some low energy subsector, is it sufficient to just draw a contour around those?
Yeah, that's very right. That's very right. That's a good point. Yeah, thank you.
What's the question? So is that okay to just draw a contour around the low energy subspace?
If I know that the state that I'm interested in lives in that subspace?
Yes, yes. Otherwise,
Yeah. Yeah, if there's gap, yeah.
You have to make sure that this contour doesn't cross.
Got it. Because in that case, you're not guaranteed that you will stay in this sector.
Right. Yeah. Otherwise, the discretized the Cauchy contour interval from there.
Okay. All right, and we also see in the first talk of our workshop, if this is all for like generic A's, for general A's, for generic solvers. However, if A has very good structure, we have seen from Soma's talk, for example, if A has the structure so that the underlying dynamics actually say all the L2 norms are preserved. In other words, the propagator is isometry. In finite dimension, isometry is essentially represented by a unitary, hence you can map it into a single Hamiltonian simulation problem. This uses the spectral structure of the problem, but here today we are talking about general solvers. Please. All right. So now let's go back to these challenges. The challenge, again, is really you have short-time numerical integrators. How do you link them together to long time? As I said, this field has already, this problem has already been considered for more than 10 years. So there already exists fantastic approaches. I want to highlight these are sort of the milestones in this paper, in this field, in my opinion. I might have missed many of the references because, yeah, it's more than a decade. But this, in my opinions, are important ones. Well, I apologize if there's some missing here. And then the previous approaches, the idea is the following. If I cannot do this, keep one time step and march to the next time step, and I have linear differential equation to begin with, and then maybe it's just a good idea, I just piece all of these time steps, these vectors together. And make it longer, well, the dimension increases. If you have L time steps, the dimension increases multiplied by L. But you don't worry that much quantumly because in the end of the day, you are going to take a log. So, well, your dimension is larger, it's probably fine. So this is the beautiful idea first proposed by Dominic Berry and followed up by many of the works. And essentially, this is the idea used by nearly all of the previous differential equation solvers to to piece together to get a long time evolution equation. Now, concretely, what you do, well, this is just showing that I'm piecing everything together. And then I have a linear differential equation. I just piece everything together, honestly write out what it is. And now then what I do, and then I'm going to apply the linear system solver quantumly. We know that the best possible linear system solver has this dependence where this S is sparsity. Well, is this guy sparse? Well, it is sparse. If you assume A is sparse, then the whole thing is OK. The second question is, what about N? Well, the original matrix size is 2 to the N. Now you enlarge it, you multiply by L, but it's in the log factor. You don't worry too much. So the only thing that you should really worry about is this condition number. So if you do go into all of the various existing works in the literature, you will see that the main technical lemma is really to estimate this condition number. Well, it turns out this condition number can be typically estimated with certain assumption, which I will discuss. to be a polynomial dependence on delta t inverse. In these cases, this alpha, for some alpha that you need to determine yourself, for these cases, this alpha equal to 1. This will enter in the end of the day the cost, giving you a time-dependent cost after you get everything. All right, so far so good? Well, you just apply this. Now what you get, I want to remind you, you are not done yet. Because what you get is this larger vectors. You are not really getting this, the final one yet. So what you need to do is from this larger vector, you do a post-selection, which is a very reasonable thing to do. Imagine it's all of the norms are the same. You could imagine the success probability is basically 1 over L because this is this much in terms of the whole thing. For general differential equations, since L2 norms are not preserved, and then you will sacrifice something, so people have invented this technique, so-called padding, which means I want to put more of the final time step here, make it longer, and then I can make the success probability nicer, and together with amplitude amplification. So this is the generic ideas of previous results. Now I would like to show you for time-dependent Hamiltonian simulation specifically, if you use QLSA, this is a state-of-the-art result in that scenario. So now I want to discuss some of the assumptions. Number one, you need a sparsity, which I already discussed why. Number two, you need to assume the coefficients is actually smooth. In particular, actually, you need it to be analytic in order to achieve a log dependency in the procedure. Well, why is that? So actually, in order in this state-of-the-art algorithm, what you do is a sort of a spectral algorithm, spectral method, which gave you spectral convergence. So we know that spectral convergence, so that's why you see that it has all derivatives, meaning you take arbitrary order derivative and you do the soups along all of the natural numbers. If that is bounded, then essentially your spectral algorithm, since the underlying solution is analytic, become a geometric convergence. In other words, it's exponential convergence. That's why the exponential convergence gives you a log dependency in the procedure. Please.
Can you go back on the slide? So when you do this padding, then you also introduce the same block in your matrix. So you set your matrix is rank deficient. Doesn't that create any problem?
Yeah, that will make this larger, but in the end of the day, you take a log of that. And to show this is still okay should be part of the technical lemma you need to do. That's a very good question. And please.
It was part of the question, like how does that change the condition number? Yeah, how does that?
Oh, yeah. So you need to, I should have said that after padding, you need to show the new thing together with padding, the condition number of that thing instead of this one, if you choose to use padding.
Oh, on the condition number, you said something about like 1 over delta t.
Yeah.
So where does A,
Alpha?
or the A1, A2, A.
Yeah. I will show you like how to bound this condition number. It's precisely in this. Yeah, thank you for the question. So this is the first assumption is the analyticity essentially guarantees the spectral accuracy becomes exponential accuracy. You may wonder, what if my solution is not analytic? In other words, it's not, it's not that all of its arbitrary order derivative has a uniform upper bound. What if it does not? So for differential equations, we know that if we have spectral accuracy, for example, if my solution is continuously differentiable up to case order, say it's in CK, and then we will have a case order convergence is coming from the spectral accuracy. In other words, this expression will become not linear in T, but a higher polynomial in terms of T, and the log dependency in procedure will become a polynomial dependence on procedure. When I say polynomial, I don't necessarily mean that the shoulder has to be an integer, but you will no longer have a log dependence if the underlying solution is not analytic. All right. So the other important assumptions typically people are making is this. I want to maybe just emphasize this dissipative assumption is actually turns out to be something that you cannot remove. We see it in this morning if you need a dissipative assumption. Basically, any existing differential equation solvers, no matter what kind you look, you need to have a dissipative assumption in order to make it work. Please.
Can I try to understand this a bit better? So you want analyticity in all variables or in the position or also on T? Like what's the first?
Yeah, in T. In T.
In T.
Yeah.
Okay, and you say the derivatives have uniform upper bound. Is it like the spatial derivative or the time derivative?
The time derivative. And the time derivative up to arbitrary order. This is ODE setting that I'm talking about. That's why I don't care about spatial derivative. So time derivative up to arbitrary order, and you soup of this order, and that is
So the derivatives cannot like keep growing with the order of the derivative.
Cannot.
No. Okay.
Cannot. Yeah. Thank you for the question. Please.
Sorry, I might have just spaced out, but what's the definition of dissipative?
Yeah, dissipative in general is that I have a propagator, or maybe from A to B, AS, DS. This guy is bounded by 1. Yeah, this is a general form of dissipation. You can also make it a sufficient condition. For example, assume the real part, what we have seen this morning. Yeah, this is in general what dissipation means. Thank you for the question. But in these cases, actually what they were assuming is that since, I talk about this. So another condition you assume, the norm of the propagator is bounded by 1.
That's a sufficient thing. You can have some transient growth with the real part.
Yeah, that's a log.
Yeah. This is maybe,
In the long time.
yeah, in the long time. In the long time. Yeah, in the long time. Thank you. Yeah. So, another assumption that is typically used in order to keep the condition number bounded is that one typically assumes A is diagonalizable for all the time, which may not always be satisfied. And on top of that, you want to assume the condition number of V has a uniform upper bounds, which actually comes linearly in terms of the complexity cost. So this is what is needed. Back to the question. So in these cases, since the system is already uniformly diagonalized, then the one sufficient condition to make it dissipative is that these eigenvalues are bounded by 0. Yeah. Thank you for the question. All right. So I think we are hopefully we are okay so far. Just want to say a little bit that these similar harmless conditions are indeed harmless in many of the cases, but may not be harmless in other cases. For example, here I just gave you a very simple example. I have an A that looks pretty simple, and the exponentiation of it seems to be okay. However, if you diagonalize it and you look at the condition number of these V's, they are actually not bounded. They can easily blow up. So this is sort of what has been noticed in literature. So Crovey, in back pre-printed last year, actually solved this problem. You can get rid of this condition number for time-independent problem. And later, after our work, we can also get rid of this for time-dependent problem. And after our work, Barry and Kosa also have a very nice solution in QLSA. You can get rid of this condition number dependence, which is a very good work. Are we okay so far? Yeah. So now, if you compare these problems together with the previous Hamiltonian simulation, you realize that first of all, this is why I have a highlight here. The analytic of these coefficients is typically not assuming Hamiltonian simulation to get a log precision dependence. Usually what you assume is that the first derivative is bounded, that is going to be sufficient. So this is more restrictive, appears. The second thing is that in the cost, you see there is this linear in Q, where in Hamiltonian simulation, you do not really have this factor. So what is this Q? It really sort of tells you what is the behavior of the solution. You may wonder, is this Q something essential? Maybe it's because we didn't cleverly design our quantum algorithm. Maybe we can get rid of this Q completely. However, it turns out it's not possible. So linear in Q is actually needed for oracles. You can find proof here, as well as what we have seen this morning at Don's talk. If you want to talk about the state preparation cost to the initial state, and it turns out you can do linear in Q, and all of the other parameters is not, you can do linear in Q, but you don't have to have T dependence and precision dependence at all. So this is, but the linear in Q is really needed. It matches the lower bound. So a natural question then is that if this is the case, linear in Q dependence, then can we achieve the better state preparation cost? I would like also refer to this morning's talk. All right. So now I can sort of summarize the two questions that basically we would like to discuss. Number one is really that if I just coming from like myself, a classical numerical analysis viewpoint, I just, isn't there a way that I can just maybe make the naive time marching strategy work? Maybe I can just somehow, I just really want to make the original time marching strategy work. The second is that if the problem have certain structures, then maybe can I get improved state preparation cost? So these will be the two questions. So I can give you an answer right away before I dive into some more details of the technicality. So the both answers turns out to be yes. So this is sort of how you can, if you don't care about the technical details, this is what our work is about. It's basically a pot. So you can view my talk today as a story of a pot. So what we are doing is basically we are giving you a pot. So you as a practitioner, maybe you have a differential equation that you have in mind, which is your veggies. You choose your favorite veggie. And then you need a meat, which is the short-time numerical integrator, where you choose whatever meat you'd like. And then you can put it in our pot, which is a time marching strategy, and we cook it for you, and I give you the long-time circuit. Well, you may ask that, is this the best possible long-time circuit? In other words, is this the best possible dish that you can make out of these ingredients? Well, very likely not. If you want to say optimal parameters of in terms of everything, perhaps you should go to a 5-star restaurant and ask a chef to make it for you. But indeed, but at least this is a working, we will give you a working algorithm, which means the dish is editable. And it actually, in many cases, comes with some nice properties, such that when we pair with truncated Dyson, we indeed have log dependence on the precision. Well, there are some things could be worse. I will show you what they are. And also, you can have for homogeneous differential equation, you can have for dissipative ones, you can have optimal state preparation cost. It's not the best in terms of everything, but at least it's something. Okay. I would like to pause and see whether you have any questions before I go into what our strategy is. Tyler, please.
So I guess this Q, that was the ratio of the initial state norm to the final state norm. What kind of conditions do I need on A so that that's not exponentially large? Or what conditions on A?
Yeah, that's a great question. But the norm of e to the TA can be an upper bound of that. Maybe your well, it can be in the eigendecomposition basis. It can be have many sub blocks. Sub Jordan blocks, and then maybe you are in the particular subspaces so that you are maybe you do not have a blow up. Maybe you are in a very bad places. You have a blow up. This just turning a for sure not working problem into something that depends on your solution. That is actually a very good question. I would also like to mention something of this form. Well, the solution dependence will also appear in classical numerical analysis anyways. So this is a reasonable. Somehow you can argue it is still something reasonable. Thank you very much. Yeah.
Just as a follow-up, there will always be decay though, right? It's just a matter of how strong that exponential decay is. Or...
may not. For example, if you have a block diagonal and one part is doing a Hamiltonian simulation, and you happens to live in that subspace, and then it's not changing. Yeah, please.
I have a question. So, well, nice dish it looks like, but if you do this simulation with the gates, do you also control Q of t so that you can output Q of t if it gets too small and say stop, you're out of control?
Yeah, this is really like although we don't really have a fault-tolerant quantum computer to actually run, but classically we also do this. We don't want to get the sharp estimate of these coefficients. I just run.
I'm asking whether your algorithm also puts out the Q of t. The length. I mean, if the length goes down, do you have an extra measurement which tells you stop here because it's too small?
Yeah, as long as you have upper bound of Q, it should be sufficient.
I want to know whether the algorithm gives you Q of t.
Oh, the algorithm do not give you Q of t. Yeah, the algorithm do not give. This is a same for classical as well. It's something that is solution dependent. If your solution is like, well, not related with differential equation, maybe even for optimization is the case. If it converges, it converges. If it not, then, well, it depends on the specific problem, whether that a parameter, how large is that parameter. Thank you for the question. Okay, now I'm going to talk about how this, the catchphrase is really time marching can work. And there are two key ingredients that I'm just going to discuss a little bit. Number one is the uniform singular value amplification. The other is a compression gadget. Well, let's go back to the original picture that I used to motivate our discussions, where if I have forward Euler, this is guaranteed to be a number that's larger than L, so the success probability is exponentially small in terms of the number of time steps. This is something we want to avoid. However, an immediate observation would be if I really, instead of getting this, if I get almost the best, the actual best subnormalization factor you can possibly get, and then you raise it to the L's power, maybe it's not so much of a problem because it approximates the whole thing. And if this guy is either unitary, then it's equal to 1, it's differentiative, and then maybe it's bounded by 1, bounded by certain constant, then you are okay. So this is really the ideas that we would like to explore and see how far it goes. So if you look at this, then what I really want to do is starting from some normalization factor, which is bad, which is something that is very large. And then I want to reduce the subnormalization factor in a way that is oblivious to the state I start with. Otherwise, I have this exponential accumulation with the state preparation. So if you look at this, this must be something that is very familiar for Hamiltonian simulation especially. This is precisely what is done by OAA. Right? If you have a unitary or something that is close to unitary, take a unitary for simplicity. And then what is a singular value of a unitary? It's 1. So you are only responsible to boost one singular value, for example, 1/2 to 1, and then you can easily construct a polynomial or the polynomial to do that. Well, this is more concretely what singular OAA is about. Essentially, if A is close to unitary, A dagger A give you identity, so you can easily implement it. It's because there's only one singular values you worry about. Now, actually, we already know from yesterday that OAA has a very nice generalization for isometries, which works for open quantum systems such as Lindbladians. The underlying viewpoint, high-level idea is really that the underlying dynamics is CPTP, so you can still tweak sort of this nice strategy to work. And then for Lindbladians, you can do UAA. However, for general non-unitary dynamics, which is not unitary, not CPTP, you really need, at least from what I know, you really need to boost all the singular value at a uniform rate, so you don't change what is the matrix that you are implementing. All right, so I want to boost all of the singular value and using up to this. And I want to do it in an obvious, oblivious way to the initial state. Then there's the immediate solutions that you might already know. That is just QSVT. QSVT is particularly designed for something like this. So what I'm going to do is essentially, I'm just going to change this as a ratio, and I'm implementing gamma x, this function, basically. All I need is to seek a polynomial approximation. You may wonder, I talk about this in the tutorial, and the very good question is, why do well, this is already a polynomial. Why do I do a polynomial approximation? It's really because in QSVT, you need a function from -1 to +1, all bounded by 1. So now if you plug in +1 here, it's gamma, and the gamma is something that is guaranteed to be larger than 1. So you cannot just use this polynomial. Instead, you want to do a polynomial approximation, and then you immediately realize that in order to pose these norm conditions, there will be Gibbs phenomenons going on. So Gibbs phenomenon tells you cannot perfectly sit at this point. There will be some overshooting that is not avoidable. So exactly due to this overshooting, we will have to sort of pay a price. We can make the polynomial lower a little bit to conquer this overshooting in order to make it to work. So this is how delta comes in. We cannot perfectly reach that point. And however, using this, we still can use things work, which is a uniform singular value amplification, which has this degrees of cost. So at each of the time step, you boost the you boost the subnormalization factor and using this trick, and this is the cost that you pay. So I just like to mention this is really a modified version of the wonderful authors in the audience. So how exactly you prove it? There are various different ways. Symptotically, they're equivalent. For example, you can just construct a rectangular function and you multiply by x, something like this, and you multiply by 1 over delta. You try to construct. There is an explicit analytic construction for this polynomial. However, just a tiny little thing that I want to mention is that this explicit construction in reality may not be the best that you want to use. Say here I compare the same procedure, and here you can see the degree of polynomial here using the explicit construction is 2000, versus here, maybe because previously we already formulated everything into basically an optimization problem, it actually turns out to be a convex optimization problem. You can easily solve on classical computer, well, this is, and you can get a degree that is only 20 versus 2000. So for the symptotic scalings are the same, but for practical reasons, maybe you want to do something different. Yeah.
So my question is going to be, is it true that the asymptotic, or that the scalings are the same, it just changes the constant factor, or is there any?
Yeah, there is some evidence. Well, because this paper is about asymptotic scaling. We don't dive into further improve the things, but this is you choose different errors. You can see that if you do the convex optimization way, it's better. And because optimization is really trying to find the best one, so it's guaranteed to be better than any constructed one by hand.
And I mean, but is there a way to see that this only changes constant factor, or does this actually change some of the scalings?
Yeah, it changes the constant factor. Yeah.
I think the more accurate analysis may be a little different. So in the very asymptotic case, it doesn't change. But there is a pre-asymptotic regime. You can still talk about some relation between delta and epsilon, and might find some asymptotic.
Yeah.
So it's a mean of something.
Yeah. Yeah, that's right.
Yeah, I feel like this is very important for any of the people interested in resource estimation, because
2020 they're different.
Yeah, that's right. Thank you very much. Yeah. So now you have things packed. Basically, if you do this, you can piece everything together. You will have a working algorithm. And you may wonder, well, I sacrifice a little delta sacrifice at every of the time step. I raise it to L's power. Isn't that give me a blow up? Well, you can choose this delta to be 1 over L, and then it will contribute something that is of order 1. But this is a sacrifice of L is indeed a obstacle that will make our algorithm dependence in terms of t is not going to be linear. This is precisely because this reason. If you can somehow magically not do this, and then it can improve. If you have any idea, please come to discuss with me. And then the corresponding circuit will just look as following. I would like to say this will be a working circuit as long as you are not so keen about using maybe amplitude amplification to further improve the state preparation cost. If you are okay with that, this is already a working circuit. But we are not quite satisfied with this yet. We still want to use amplitude amplification in order to get a better state preparation cost. So you can imagine if this is the case, well, what's preventing us from doing amplitude amplification is really just because it's not coherent. There are mid-circuit measurements. You can imagine I can defer the mid-circuit measurements, but then it will introduce a bunch of ancilla that may not be optimal. You can use the product of the block encoding, get the block encoding. It will also give you a lot of ancilla. So a very natural idea is then to do a compression gadget, which essentially count whether this is successful or not. The point is really that you get away with log of L ancilla instead of a larger number. So this log in terms of L is something that we are more happy with. So in the end, you can estimate the success probability, and this is a Q. I will discuss what Q is later. And the round of amplitude amplification is of order Q. Please. Thank you. Yeah. Now this is essentially our core theorem. So it's very difficult to look at, but the point is that you as a practitioner, you are responsible to come up with your differential equation and your integrator, and you construct a block encoding of your short time integrator only, and we give you a working circuits for the long time integrator. We call you what is the cost. So maybe this is easier to look at. It's really that you give me the ingredient, we have a pot and we cook it for you. It's a dish. Is it best dish? Well, probably not. For some parameter it will be yes, but for some scenarios maybe not. So now I just want to discuss some concrete examples. One is a high order convergence. I may not discuss the low order for the interest of time. So one is a high order numerical integrator, which is truncated Dyson. We know it has exponential convergence and so on. The second is a low order integrator. The point of this is really our pot is independent of ingredient. Whatever ingredient you throw it should all work. It doesn't matter whether it's a high order or low order. Well, this is when we paired with truncated Dysons that we have seen in the workshop perhaps many times. And the point is that the algorithm will have the following cost. You can see that it's log dependency on the precision. The time dependency is not optimal. It becomes t squared. We cannot get to linear in t precisely because this sacrifice in terms of delta. And then this, you may wonder, what is this Q? This Q sort of really quantifies how far away your dynamics is from unitary. If you imagine your dynamics is unitary, then this quantity is 1. If the dynamics is dissipative, this is upper bounded by some Q, which is a Q that I discussed previously. And a nice thing to discuss, to look at this algorithm is really that there's no assumptions of the A needs to be diagonalizable at all time and the upper bound in terms of V. You also do not need an analyticity of A in order to achieve a log dependency in the precision. So this is, we only need a bounded variation, and the bounded derivative is sufficient condition to, for bounded variation. All right, so now you may ask, well, is this Q really needed here? It turns out you can prove, so far we are not assuming any dissipativeness. You can prove that this is actually linear in Q is the lower bound. It essentially is the lower bound. And then in the dissipative cases, I'm assuming, suppose this is bounded by 1, this is sufficient condition for dissipative. And then correspondingly, the cost will become a lower case of Q. And we have seen in this morning and together in this very nice paper that this matches the theoretical lower bound if you indeed have this case. All right, so this is for the high order integrator if you want to use. Correspondingly, you say, okay, I have my own Fourier integrator. Maybe it's just first order. Does it still work? Well, there are various different first order integrator. We decided to choose this in our paper for demonstration purposes, really because when we use it for Hamiltonian simulation, it turns out in high precision that we are considering, it has a commutator scaling in front of it instead of the norm of A itself. The commutator scaling is sort of nice, so we just use this, but this the particular integrator again is not the point of this talk or this work. It just shows you this works. But as you can see, the scaling may not be the best. For dissipative cases, you still have optimal state preparation cost. However, if you look at this, it looks fairly bad because it's no longer linear in T, not even quadratic in T, and so on and so forth. This is really because you are using a first order algorithm, and in the error estimate, basically you have some T squared divided by L. This is capital letter T divided by delta T from my numerical analyst. This might be natural to you. That is essentially epsilon. In other words, this L comes with T squared scaling. And since our algorithm sacrificed by delta, this gave you a L squared cost. That's why you have this T to the fourth. So I'm just saying, well, you may still, using our pot, you may still have optimal state preparation for homogeneous differential equation, but this will depend on the problem and depend on what is the numerical solver you choose. And let me skip all of that. The final thing is that I gave you a pot. That's the whole point, the story of a pot. And yeah, as a practitioner, maybe you have a real problem. Please welcome to use our pot to cook it. And then the open question would be, can you improve T squared to T? And in the time matching strategy, we don't have a good way to address that. If you have any idea, please come to me. Especially, can you find a better way to boost this success probability? And another question is, for inhomogeneous differential equation, in the end of the day, we can do a LCU, but can you do without a LCU in the end, still in a time matching way? Both are very nice open questions. With that, I want to thank you for your attention.